So electrophoretic technique is also a chromatographic, non-chromatographic technique. It doesn't require any stationary phase and mobile phase, but it is a highly powerful separation tool or separation technique, which is used for the separation of variety of the species which are present in different samples. Whether the sample may be containing solutes of simple molecular weight or larger molecular weight, whatever it is, we can easily separate the solutes by electrophoretic technique. So, under this lecture, we shall understand about the meaning of electrophoresis. How do we classify the electrophoretic techniques? What are the theoretical backgrounds of this electrophoretic technique, particularly the electrophoretic mobility, electro-osmotic mobility, and along with the electrophoretic and electro-osmotic mobility, what is the total mobility of the species? So, what is the time required by the solute for its movement during the separation process, that is called as migration time? How do we describe the efficiency of separation process of electrophoretic technique? And how do we describe the selectivity of electrophoretic technique? And what are the factors deciding the electrophoresis separation? And what are the resolution factors in order to satisfy the separation process for a variety of the solutes? This is going to be the overview of my today's lecture. First, let me explain the meaning of electrophoresis. So as you can see here, this is a separation technique which is used for the separation of solutes containing positively charged species, negatively charged species, and neutrals. Any sample you consider that may be contained with cations or anions or even neutral species which are going to be chargeless. So this electrophoretic technique is equally employed for the separation of not only cations or not only anions, but under specially modified conditions, the neutral species can also be separated by this electrophoretic technique. But most commonly, the cations or anions are more easily separated by means of this electrophoretic technique. So here, any sample containing solutes such as cations, anion, and neutral species are subjected to movement in a conductive medium. When you apply the electric field to the conductive medium, the cations which will start to migrate towards the negatively charged cathode. So you can see here from the sample or from the group of solutes, all those cations which are indicated by Mn plus, they will start to migrate towards the negatively charged cathode, and this migration is with respect to the cationic migration. On the other hand, and in contrast to the migration of the cations, all those anions which are negatively charged will show the migration towards the positively charged electrode, which is called as anode, and this is called as anionic migration. So this migration or this movement, this journey of the ions will be expected only you subject the sample for the separation of the solutes based on their charges. So the meaning of electrophoretic technique can be stated in this manner. It is a technique which is used to separate the analytes based on their ability to move through a conductive medium. Particularly, the most commonly used conductive medium will be an aqueous buffer. The aqueous buffer will be used in either lower concentration or higher concentration. Here you have to make sure that the ions of the buffer solution must not move along with either cations or anions. So that is also called as some special type of movement, some special type of migration that we shall see later. So you take a medium which is immobilized with the aqueous buffer, and this aqueous buffer has been immersed with the two electrodes. So one is positively charged electrode and another one will be negatively charged electrode. Positively charged electrode and negatively charged electrodes are connected to the power supply device. So the positive terminal having electrode is anode and the negative terminal having electrode is going to be cathode. So when you apply the electric field of any magnitude, and that is going to be denoted by E. So under that applied electric field, under that applied electrical energy, the solutes will show different migration towards their own electrodes. Say for example, cations are going to travel towards the cathode and anions are going to travel towards the anode. So cationic and anionic movements we can see obviously, but under some special circumstances, even neutral species can be made to move towards either cathode or anode. So we shall see that later. So you remember about the meaning of electrophoretic technique. Electrophoretic technique is a separation technique which is used for the separation of analytes based on their movement in a conductive medium, particularly an aqueous buffer, under the influence of applied electric field. So if you look at the classification of electrophoretic techniques, this can be classified into several types. Out of those several types, I have presented here some very importantly used electrophoretic techniques for the separation of variety of group of solutes. Say for example, slab gel electrophoresis, capillary electrophoresis. So under capillary electrophoresis, various capillary electrophoretic techniques can be described, and mainly capillary zone electrophoresis, micellar electrokinetic capillary chromatography, capillary gel electrophoresis, and capillary electrochromatography. So here slab gel electrophoresis is different from all other electrophoretic techniques, and except the first one, all other electrophoretic techniques are performed using a capillary tube. Here in slab gel electrophoresis, we don't use any capillary tube, but we will use a slab, and in between two slabs, gel is going to be immobilized. So over the pores of the gel, the migration or the movement, the journey of the solute molecules can be expected. So this is about the classification of the electrophoretic techniques. One is going to be slab gel electrophoresis, and which do not require any capillary tube, and all other electrophoretic techniques mentioned here will be performed by means of a capillary tube. Just like a column, what we will use in chromatographic technique, here capillary tube will be playing very important role. So capillary electrophoresis, capillary zone electrophoresis, MECC or MECK, even we can say micellar electrokinetic MEKC or MECK. All these are synonyms to represent micellar electrokinetic capillary chromatography. And capillary gel electrophoresis we will perform, and capillary electrochromatography we will also perform. So let us look something about the slab gel electrophoresis. So here, as I told earlier, in the slab gel electrophoretic technique, a buffer solution, which is said to be as conducting buffer, is going to be retained within the porous gel of agarose or polyacrylamide. Mainly, the agarose or polyacrylamide will be immobilized in between two glass slabs. If you don't have glass slabs, even you can use plastic slabs. So you place the glass slabs or plastic slabs either vertically or horizontally, and these two slabs are going to be separated by means of a spacer. So in between these two glass slabs, the gel is going to be immobilized, and the typical thickness of the gel is going to be 0.25 to 1 millimeter. So this gel is having direct contact with the buffer solution. So in the buffer solution, there is a provision to introduce the sample solution. So once the sample is introduced, and after the application of the electric field, electric energy, the relative movement of the cations and anions can be expected. So this is going to be done in slab gel electrophoresis. And this slab gel electrophoretic technique is highly popular in biochemical laboratories, especially for the separation of DNA fragments. The sequences of DNA can be easily separated by means of this slab gel electrophoresis. Because of his popularity for the separation of DNA fragments, it is applicable only for the qualitative analysis, especially even the solutes present in complex mixtures can be easily separated, and therefore it is not applicable for the quantitative analysis. So in order to analyze a sample for its quantitative information, we must need an output so that that output can be converted into quantity. And there is no any such parameter can be obtained by means of this slab gel electrophoretic technique. So slab gel electrophoretic technique is commonly used in biochemical laboratories, especially for the qualitative analysis. Here you can see a picture in which how the slab gel electrophoretic separation of the solute is going to be done. You see here, this is a tray, which is filled with the buffer, aqueous buffer solution, as I showed here. And there are two glass slabs you can see here. First glass slab and the second glass slab. In between the glass slabs, in between the two glass slabs which have been immersed into the buffer, into the tray, a gel is immobilized. The gel may be agarose or cephorose or polymethacrylate or polymethacrylamide or polymethacrylic acid, whatever it is. This gel is going to be immobilized in between these two glass slabs, and the thickness of the gel you have to make sure it will be probably from 0.25 to 1 millimeter, 0.25 to 1 millimeter thickness. And there is a provision of introducing the samples into this sample wells. You can call them as sample wells here. Number of sample wells are present here. So by means of a syringe or by means of any object such as a dropper or a capillary tube, you can introduce the supernatant solution of the sample into these sample wells. Okay. These sample wells are also connected to the buffer solution. The sample wells are also connected to the buffer solution. So at the bottom and the top, buffer solution must be present there. Buffer is as important as the gel because it is going to function as a conductive medium into which we are going to apply the electrical energy. So this buffer is not only having the connection to the gel, but also to the sample holder, but also to the sample well. So two electrodes are commonly present here. One will be negatively charged electrode and the other one will be positively charged electrode. The negatively charged electrode will be called as cathode and positively charged electrode will be called as anode. So when you apply an electrical energy by applying a direct current potential of 30 kV or 20 kV or 50 kV, whatever it is, the migration of the solutes through the pores of the gel will be initiated. And the separation order is dependent upon some theoretical background. I will let you know what is the theoretical background later in a couple of minutes. So, whatever the cations present in the sample solution will start to migrate towards the negatively charged cathode, and whatever the solutes which are carrying the negative charge, they will start to migrate towards the positively charged anode. So this relative migration is dependent upon the couple of factors with respect to those solutes. Let us understand them later. So this is how the slab gel electrophoretic separation is going to be performed. Here you need two slabs. Those two slabs are connected with the buffer at the top and the bottom, and these two slabs are separated by a spacer. In between these two slabs, the slabs may be plastic or glass, whatever it is. If you are going to use glass, that must be borosilicate glass because you should not have any selenal groups. Those selenal groups, glass is made by silica and silica is very rich in selenal groups. Those selenal groups must be deactivated by chemical treatment. So that chemically treated glass material can be used in order to perform a slab gel electrophoretic separation. So you create the slabs in such a way that the gel has been immobilized in between the two slabs at a thickness of 0.25 to 1 millimeter, and this gel is having getting connected with a sample well, so that into these sample wells the samples are going to be introduced. So this may be a dropper, or this may be a capillary tube, or this may be a micro pipette, or this may be a conventional pipette, whatever it is, through which you can introduce the sample. So you apply a direct current potential by means of a power supply device, then introduce the sample. Dependent upon the relative migration rate of the solutes which are positively and negatively charged, the solutes will start to show their relative migration towards either cathode or anode. So based on this, the solutes are going to be separated. Here, there is no scope for separating the neutral species. Neutral species will be eluted as a single band, and we will be unable to arrange them with respect to their elution order. So whether you are performing gel electrophoresis or capillary electrophoresis, whatever it is, the elution order for the neutral species cannot be interpreted. But under some special circumstances, we can do that also, that we shall discuss later. So this is about the slab gel electrophoresis. So let us move on to the capillary electrophoresis. So as the name is implying that in capillary electrophoretic separation process, we will be using a typical capillary tube, and the capillary tube will be acting like a medium, acting like an object, which is going to be used to retain the buffer solution, where the buffer solution will be acting like a phase in which the solute migration can be expected. So in slab gel electrophoresis, buffer is also present there also, but buffer is present at the top and the bottom, and between the top and bottom portion of the buffer, the gel is going to be immobilized, and through the pores of the gel, the solute molecules will migrate. Here, buffer is retained in the capillary tube, and the capillary tube will be having a typical inner diameter, particularly from 25 to 75 millimeter. You take any capillary tube is also made by silica. I will show you what is the structure of the capillary tube and how it is going to be constructed. What are the various features of the capillary tube? Let us discuss that later. So you take a capillary tube. Capillary tube is going to have a internal diameter, particularly in the range from 25 to 75 millimeter. So into the capillary tube, the conducting buffer is going to be retained. So capillary is having two terminals, first terminal and the second terminal. At the first terminal, along with the buffer, sample is going to be connected to the first terminal of the capillary tube, and the other terminal will be connected to the detector, then ultimately to the destination reservoir. So sample is injected into the capillary tube from the one end. Sample solutions are going to be introduced to the one end of the capillary tube, either by using any injectable object. So soon after the introduction of the sample into the capillary tube, because the electric field is generated there, in the presence of the generated electric field, the solutes are going to migrate towards either cathode or anode. This migration is plotted as a function of the time, and this plot is called as electrophoregram. So this is resembling with the chromatogram in chromatographic techniques. Chromatogram is nothing but it is a graphical representation of the detector signal versus the time at the volume of the eluent. If you plot the detector signal versus the time, the x-axis is going to give you the retention time for each and every solute at which the solute is eluted soon after introduction of the sample into the chromatographic column. Here in the electrophoregram, same detector can also be used, and the detector is going to be responded after the solute molecules individual reach out 8, and some function of those solutes will be plotted as a function of the time taken by those solute to reach the detector, and this graphical representation is called as electrophoregram. So just like chromatogram, because that can be used to obtain qualitative and quantitative information in chromatographic techniques, electrophoregram is also very, very useful for both qualitative and quantitative information. So capillary electrophoretic separation of the solutes will be done by means of a capillary tube, which is filled with a buffer solution, aqueous buffer solution of appropriate ionic strength. So after the introduction of the sample, the solutes present in the sample will cause the relative migration towards either cathode and anode. But the neutral species can also be made to migrate in the capillary tube, that we shall see later. So this is called as capillary electrophoresis. Here you can see how the capillary electrophoretic separation is going to be performed. So this is going to be the capillary tube. This is arc type object what I have presented here is going to be the capillary tube. This capillary tube is presented here for its cross-sectional view. The idea of the capillary tube, let it be 25 to 75 micrometer, 25 to 75 micrometer. And the outer surface of this capillary tube has been coated by polyamide. Because of this polyamide coating, it will impart the brownish color. It will impart the brownish color. So, because this is made by fused silica, from the circumference to the outer circumference of the capillary tube, the thickness will be around 330 micrometer. Thickness from here to here, the thickness will be 330 micrometer. This thickness is also matter here. Not only the internal diameter, but also this thickness is also matter here. So let us see how it is going to play a significant role. As the thickness is increased, what is going to be happen? As the internal diameter is increased, what is going to be happen? Let us see that later. So a capillary tube is connected particularly for two reservoirs. One reservoir is called a source reservoir and the other reservoir is called as destination reservoir. To the source reservoir, there is a provision to introduce the sample solution directly. There is a connection between the sample reservoir and the source reservoir. So, the electrode which is going to be connected to the positive terminal of the power supply device is called as positive electrode, that is anode, that is immersed into the source reservoir. And the cathode which is negatively charged electrode, that is going to be immersed into the destination reservoir. So, capillary tube is immersed into source reservoir and the destination reservoir. One end of the capillary tube is connected to the source reservoir followed by the anode, and the other terminal of the capillary tube has been immersed into destination reservoir. Now both the electrodes have been connected to the high voltage power supply device ranging from 0 to 30 kilovolts. 0 to 30 kilovolts will be the commonly employable potential difference. So once the sample is introduced, under the influence of the applied electric field, the solutes present in the sample will start to migrate, particularly the cations. From this source reservoir to the destination reservoir, cations will start to migrate, and during the migration, they will fetch the detector, and the detector is going to give you the signal with respect to the solute. All those detectors what we will use in HPLC and GC can be used in capillary electrophoresis also. So this is how the separation is going to be performed in capillary electrophoresis. So two reservoirs are required. One will be the source reservoir and the second one will be the destination reservoir. Source reservoir has been connected with the sample reservoir and the sample reservoir is having direct contact with the anode, but anode is not immersed into the sample reservoir. Under special cases, anode can be directly immersed into the sample reservoir, provided the sample is soluble in the buffer what you are going to employ in order to perform the separation process. So in those cases, anode can be directly immersed into the sample reservoir. So sample reservoir, source reservoir and anode, they are interconnected. And one terminal of the capillary tube is immersed into the source reservoir. Other terminal is immersed into the destination reservoir. In between the source reservoir and the destination reservoir, there is a detector. So this detector will be relatively functioning with respect to the migration of the solute molecules after the electric field is initiated. So this is how the capillary electrophoretic separation is going to be done by means of capillary tube. So while performing the separation of the solutes by capillary electrophoretic technique, it is very essential to understand the theoretical aspect. So what is the theory of capillary electrophoresis? We need to separate the solute molecules or the solutes which may be charged or uncharged, which may be neutral, which may be acidic or basic, whatever it is. They might be having a lower molecular mass, or they may be macromolecules, whatever it is. After the introduction of the sample into the capillary tube, they will be separated based on their capability in order to migrate in the conductive medium. So the sample is going to be injected into the buffer solution. That means to say that into the capillary tube. Capillary tube is immobilized or retained the buffer solution of some ionic strength. So soon after the introduction of the sample into the capillary tube, the electric field is going to be generated. So after the electric field is generated, the sample components will start to migrate, and this migration is result of two types of mobilities. One is going to be electrophoretic mobility and the other one is going to be electro-osmotic mobility. So the electrophoretic mobility is denoted by nu EP and the electro-osmotic mobility is denoted by nu EOF. Electro-osmotic flow or electro-osmotic mobility denoted by EOF. So what is the meaning of electrophoretic mobility? And in contrast to that, what is the meaning of electro-osmotic mobility. So let us see the meaning of electrophoretic mobility. The electrophoretic mobility is with respect to the mobility of the solutes in response to the applied electric field, nothing other than that. The moment you create the electric field, the moment you apply the direct current potential to the capillary tube, the solutes, dependent upon their relative affinities, they will start to migrate. This solutes migration is called as electrophoretic migration. So the solutes response in respect to the applied electric field is called as electrophoretic mobility. Particularly, when you apply the electric field, cations will start to migrate towards the cathode because cathode is negatively charged, and the anions will start to migrate towards the anode. So there will be a tendency to measure the solute's ability to move towards either cathode or anode, followed by the conductive medium. This is called as electrophoretic mobility. So electrophoretic mobility is nothing but it is a measure of the solute's ability to move through a conductive medium in response to an applied electric field. The moment you apply the electric energy, the electric field to the capillary tube, cations will start to migrate towards the cathode, which is negative electrode, and the anions will start to migrate towards the anode, which is positive electrode. Whereas the neutral species do not show any migration, do not show any mobility, do not show any movement. So they remain stationary. There is no question of explaining the ability to make the neutral species to make movement. We cannot make the neutral species to move. So only we can expect the movement of the cations and anions towards either cathode and anode. Therefore, this mobility is called as electrophoretic mobility. So you can see here, electrophoretic mobility denoted by nu EP can be defined as soon after the application of the electric field to the capillary tube, a measure of a solute's ability to move through a conductive medium in response to an applied electric field is called as electrophoretic mobility. In contrast to the electrophoretic mobility, electro-osmotic mobility is also very, very important. What is this electro-osmotic mobility or electro-osmotic flow? This electro-osmotic flow will occur when the buffer solution will start to move through the capillary tube. So when you apply the electric field, we will be anticipating only cations and anions to move through in the capillary tube in the buffer medium. But buffer solution is also containing some ions. Those ions will also start to move. The ions of the buffer solution will also start to move towards the cathode under normal condition. So not only the cations of the buffer solution, but also some anions of the buffer solution will also start to move towards the negatively charged cathode. So this movement is called as electro-osmotic movement or electro-osmotic mobility or electro-osmotic flow. So this electro-osmotic flow will occur when the buffer solution moves through the capillary in response to the applied electric field. Under the normal conditions, the buffer solution will be probably moving towards the cathode. It not only move towards the cathode, but also it will be sweeping out most of the solutes, even anions, towards the negatively charged cathode. This movement of the buffer species towards in the conductive medium towards the cathode is called as electro-osmotic movement or electro-osmotic mobility. This is denoted by nu EOF. This can be defined as the movement of the conductive medium in response to an applied electric field is called as electro-osmotic flow or electro-osmotic mobility. So now you must be able to distinguish electrophoretic mobility and electro-osmotic mobility. So electrophoretic mobility is nothing but it is the measure of the ability of the solute's movement in a conductive medium under the influence of the electric field. This is called as electrophoretic mobility. The electro-osmotic mobility is nothing but it is a measure of the ability of the species of the buffer solution to move in a conductive medium under the influence of electric field. So this is how we can distinguish the movement of the solutes and the movement of the species of buffer solution. So during the electrophoretic mobility, each and every solute will be moving with its own velocity. That velocity is called as electrophoretic velocity. Electrophoretic velocity. This electrophoretic velocity is with respect to the solutes. With respect to solutes, not with respect to the species of buffers. So this is denoted by VEP. The electrophoretic velocity is denoted by VEP. That is related with the magnitude of the electric field strength E, denoted by E, and the electrophoretic mobility. So the electrophoretic velocity of any solute means the velocity with which a solute is moving in the capillary tube is called as electrophoretic velocity. When you introduce the sample to the capillary tube, the solute molecules will start to migrate towards either cathode and anode, especially cations or anions. So at what velocity the cations and anions are moving, that velocity is called as electrophoretic velocity. So electrophoretic velocity is denoted by VEP. That is a product of the electrophoretic mobility and the magnitude of the electric field strength E. So VEP is equal to nu EP into E. So if you simplify, we will get an expression nu EP is equal to Q by 6 eta into R. This is a very, very essential and useful expression in order to express the relative mobilities of the solutes, either cations or anions, and even neutral species. Where Q is nothing but, it is simple to define Q, it is a charge on the solute. If it is a cation, +1 for monovalent, +2 for divalent, +3 for trivalent, +4 for tetravalent species. So Q is going to be the charge of the solute which is migrating towards either cathode or anode. Eta is very important here. This is going to be the viscosity of the buffer medium. We will prepare a buffer solution and that will be retained in the capillary tube. What is the viscosity of that buffer solution? That is denoted by eta, where R is going to denote the size of the solute, radius of the solute, radius of the solute. So the charge on the solute and the radius of the solute, these two factors are more than enough to decide how the electrophoretic mobility is dependent. So if you look at this equation, the electrophoretic mobility is solely dependent upon the charge to size ratio. Charge to size ratio. Say for example, if a sample is containing monovalent, divalent and trivalent solutes, cations or anions, whatever it is, if you introduce them to the capillary tube, say for example, you take lithium, you take calcium, you take aluminum, and you take thorium. Monovalent, divalent, trivalent, and tetravalent species have been introduced to the capillary tube. The capillary tube is retained with a buffer solution of viscosity eta. So lithium, calcium, aluminum, and thorium, they have their own radius. They have their own particle size. So the electrophoretic mobility of lithium, because lithium is positively charged species and it is monovalent species, the value of Q will be +1 and the value of R for lithium will be high because it is lower charged and size is definitely going to be very high. If any species having lower charge, size will be more. Size will be more. So lower charge, higher size. So the electrophoretic mobility is definitely going to be lower. So the electrophoretic movement of lithium ion will be lesser when you compare with the electrophoretic mobility of calcium 2+, because calcium 2+ is divalent, Q will become 2+, and the value of R will be lower than the R value of lithium plus. Therefore, Q by R value will become more. Therefore, nu EP of calcium 2+ will be more than the nu EP value of Li plus. Similarly, nu EP value of aluminum 3+ is lower than nu EP value of calcium 2+, and ultimately the electrophoretic mobility of thorium 4 plus will be greater than the electrophoretic mobility of aluminum, calcium, and lithium. So, which species is going to exhibit the greater electrophoretic mobility? Thorium 4 plus is going to exhibit the greater electrophoretic mobility because that is having positive charge, and it is highly charged. Thorium 4 plus is highly charged, which is having smaller size, So the separation order can be depicted in such a way that all those species which are having higher charge and lower size, their electrophoretic velocity will be higher. So they will be moving at a faster rate. So the separation order or the elution order in capillary electrophoresis is completely dependent upon the charge to size ratio. If the charge to size ratio is very low, the electrophoretic velocity will be ultimately very low. And as a consequence of this lower electrophoretic velocity, the electrophoretic mobility of the solute will also be low. And definitely that is going to be coming out of the capillary tube at last. So whatever the solute which is having higher charge, say thorium 4 plus, next aluminum 3 plus. So like this, if the charge to size ratio is more, definitely the electrophoretic velocity and thus the electrophoretic mobility of that species is going to be more, and that solute will be eluted rapidly. So if Q is positive for cations and negative for anions, these species migrate in opposite directions. +1. In place of +1, you put -1. The new EP value is going to be very, very less. That's what anions are going to be eluted at last. So when you introduce the sample solution containing cations, neutrals, and anions, first the solutes which are positively charged are going to be eluted one by one. Then the neutral species will be eluted, or they may remain stationary without getting eluted. And at last, the anions are going to be eluted. So why neutral species will remain stationary? Because they are chargeless. They neither positively charged nor negatively charged. The value of Q will become 0. Therefore, VEP or new EP will also become 0. Therefore, they remain stationary with the value of new EP of 0. So this is the important theory of capillary electrophoretic separation. The separation order is completely dependent upon the charge to size ratio. Even if you take anions, say for example, chloride, monovalent, -1, sulfate, 2 minus, phosphate, PO4, 3 minus. So phosphate, charge is very low, sulfate, higher than phosphate, chloride, higher than sulfate. So if you subject the mixture of chloride, sulfate and phosphate, chloride is going to be the species eluted first, then sulfate, then phosphate. Because the Q by R value of chloride is more than the Q by R value of sulfate, than the Q by R value of phosphate. So for anions, similarly, the smaller charged and higher size solutes are going to be eluted at last for anions. For cations, highly charged solutes and solutes of smaller size are going to be eluted rapidly. But the same species highly charged and solutes of smaller size, they are going to be eluted at last with respect to anions. So this equation is very prominent equation in order to express the relative movement of the solutes in a conductive medium, particularly in capillary electrophoresis. And it is very, very essential to understand the theory of electro-osmotic mobility, because one should be very aware about the electro-osmotic mobility. Without the knowledge of electro-osmotic mobility, we cannot appropriately understand the theory of electrophoretic separation. What is this electro-osmotic mobility, which is denoted as nu EOF? So, we will be using capillary tube in order to perform the separation in capillary electrophoresis. Capillary tube is mainly made by silica. So the walls of the capillary tube is containing SiOH group. So the structure of capillary, structure of silica. silica is attached by the OH groups. There are a number of OH groups will be present in silica moiety. So if this silica is very rich in OH groups, those OH groups attached to silicon of the silica. So this is called as silanol groups. When the electric field is applied, when the capillary tube is charged by applying the electric field, and when you assume the pH of the buffer solution is in between 2 and 3, because the medium is acidic, and silanol groups will be definitely tend to undergo ionization, so that the silanol will be converted into selenate anions at pH in between 2 and 3. So what will happen if these selenate groups are formed? The selenate groups are negatively charged. So the exterior of the capillary tube, within the tube, the outer surface of the capillary tube is negatively charged. So it is in the need of positively charged species. It will be attracting the positively charged species, and those positively charged species will be probably from the buffer. So the cations or positively charged species, cations from the buffer are attracted towards these selenate anions. So all those cations, some of the cations of the buffer will be attracted by the selenate anion. So they will tightly bind it with these selenate anions, and they will form their own layer. That layer is called as inner or fixed layer. The binding between the selenate anion of the capillary tubing and some cations of the buffer is a consequent for forming an inner or fixed layer. Okay. Then the other cations are more loosely bound. They are floating. They are floating above this inner or fixed layer. This layer is called as outer layer or mobile layer, because these other cations, other than the cations which are bounded to the selenate anions, all these cations are freely moving. Therefore, they are present in a single layer. That layer is called as mobile layer, outer or mobile layer. So together, this inner layer or a fixed layer and outer or mobile layer, we can call these two as double layers, electrical double layers. So the cations in the outer layer migrate towards the cathode, whatever the cation present in the outer layer, because they are in motion, they are in movement, they are positively charged, they will start to migrate towards the negatively charged cathode. So, and because of the solvation of these cations, the solution is also pulled along towards the cathode in a flow called as electro-osmotic flow. So the electro-osmotic flow is arised due to the movement of the ions of the buffer in the conductive medium, and this is because of the behavioral function of the silica, which is used to construct the capillary tube. You can understand in a more appropriate manner by means of this particular slide here. So this is going to be the capillary wall. Capillary wall is containing silanol groups. If you assume the pH of the buffer is in between 2 and 3, all those silanol groups are going to be converted into selenate anions. So SiO minus, that O minus charge I have written in this manner. O minus, 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 minus. So buffer medium is immobilized in the capillary tube, and the capillary tube is charged by applying the electric current. So the ionization of the buffer has also been taken place. Due to the ionization, positively charged and negatively charged species are formed in the buffer medium. So some of the cations from the buffer are attracted by the selenate anions. Some of the positively charged cations of buffer are attracted by the selenate anions. Here you can see. So they had strong interaction with these selenate anions in order to form a fixed layer. And this layer is also called as inner layer. Next to this inner layer, apart from this inner layer or above this inner layer, all other cations along with the anions of the buffer are present. And these are present, some of the cations are present in the mobile layer. Or this is also called as outer layer. In combination, this mobile layer and the fixed layer are called as double layer or double layer. So, in the bulk of the buffer medium, all other positively charged species will tend to migrate towards negatively charged cathode. So, some cations are bonded to the selenate anions. Some cations are present in the mobile layer and some cations are present in the bulk solution. So, these cations will start to migrate towards the cathode, which is negatively charged. So this flow is called as electro-osmotic flow. This is also in the same direction. All those positively charged species along with the sample plug will show the migration towards the negatively charged cathode. So this is called as electro-osmotic mobility. And this electro-osmotic mobility is highly disadvantageous. And we have to concentrate on how to deactivate or how to reduce this electro-osmotic mobility. So electro-osmotic flow or electro-osmotic mobility is connected with the velocity of the ions of the buffer. So that is denoted by electro-osmotic flow velocity, which is represented by VEOF. VEOF. So just like VEP is equal to nu EP into E, we can write VEOF also. VEOF is equal to nu EOF into E, where VEOF is the electro-osmotic flow velocity. This is a velocity with which the solute moves in response to the applied electric field. Ions of the buffer will move. The ions of the buffer will move in response to the applied electric field is called as electro-osmotic flow velocity. So this is simply the product of the electro-osmotic flow and the magnitude of the electric field strength. So nu EOF into E is going to give you VEOF, and nu EOF can be written as epsilon into zeta divided by 4 pi into eta. So just like nu EP is equal to Q divided by 6 eta into R, here nu EOF can be written as epsilon into zeta divided by 4 pi into eta, where epsilon is the dielectric constant of the buffer because it is a liquid, so it should possess some dielectric constant. The electro-osmotic flow is directly concerned to the dielectric constant of the solvent of the buffer or any solution which is present in the conductive medium. And Z is called as zeta potential. Zeta potential. Zeta potential is nothing but the change in potential across a double layer, because electrical double layer has been formed. Combination of positive and negatively charged species will become responsible to change the potential across the double layer, and that change in potential is called as zeta potential. This is dependent on two important factors. Let us see that in the next slide. And eta is again the viscosity of the buffer. So whatever the buffer you are going to use, the viscosity of the buffer is denoted by eta. So if you look at this equation, the electro-osmotic flow will become very high as the value of zeta is high. This value of zeta will be high whenever the ions of the buffer will involve in the migration, will involve in the process of movement in the capillary tube to a major extent. If the extent of movement of the ions of the buffer is more, then nu EOF will be greater consequently. So zeta potential will also decide. And viscosity, you have to use a buffer of or we can say a higher viscosity, buffer of higher viscosity, so that nu EOF will become low. So we can suppress by using buffer of higher viscosity, and by using the buffer which will become responsible to generate a lesser value of the zeta potential, and buffer which is also having lower dielectric constant will also become responsible to generate lower nu EOF, so that electro-osmotic flow can be reduced to the maximum extent. So as I told you, the zeta potential is because of the two factors. What are those two factors? And then the electro-osmotic velocity. So as you saw in the previous expression, if the zeta potential is more, the electro-osmotic velocity will also become more, and electro-osmotic velocity is more, electro-osmotic mobility will also become more. So As you saw in the diagram to show the movement of the cations and anions, the zeta potential is directly proportional to the charge on the capillary wall, because the positively charged species are going to be binded with the negatively charged selenate anions. Therefore, the change in potential at the double layer will be more. Therefore, zeta potential will be more. Then the electro-osmotic flow will also become more. So, the zeta potential will be very high if the thickness of the electrical double layer is high. If there are more number of selenate anions are present, the zeta potential will also become more. So, more importantly, most probably, if the pH of the buffer is around 2, at this particular pH, selenal groups undergo ionization very easily and more prominently. So, there is a more possibility for attraction of cations from these selenate anions. If you maintain a pH of less than 2, the ionization of the selenal group will become difficult. So SiOH group will remain as SiOH group only. There is no question of forming SiO minus group. SiO minus groups are not going to be formed if the pH is very low. If the pH is acidic, under the acidic pH, say for example at less than 2, selenal groups are not going to be ionized. They will be retained with SiOH group. So there is no question of explaining the movement of the cations towards the selenate anions. So zeta potential will be 0 and hence the electro-osmotic flow velocity will be 0 at pH below 2. If you increase the pH above 2 or 3, the ionization of selenal groups will become practical. SiOH group will be converted into SiO minus group, and this SiO minus group will become prominently responsible for attracting the cations which are present in the buffer, so that the electrical double layer is going to be formed, and hence the zeta potential will become very high, and consequently the electro-osmotic flow will also become more. So the zeta potential is directly proportional to the pH, we can say. And the nature of the capillary wall is also dependent, is also in the clutches of the pH factor. If pH is less than 2, SiOH group is intact, no ionization of selenal groups takes place, so zeta potential and hence the electro-osmotic flow velocity will be 0. At higher pH, ionization of the selenal groups will be taken place, and as a result of this, SiO minus groups will be tightly bonded with some cations of the buffer, thereby the creation of the double layer is possible, and hence the zeta potential will be more, therefore electro-osmotic flow velocity will also increase. And the second factor is the thickness. More the number of ions present in the buffer, more the thickness of the electrical double layer. So, more the number of ions present in the buffer, more the thickness of the electrical double layer. If you use a buffer which is having higher ionic strength, increased ionic strength you use, and the number of selenal groups present over the surface of the capillary wall will become insignificant. If the ionic strength of the buffer is more, means highly concentrated buffer you have used, infinite concentration you say 5 molar, 6 molar, 7 molar, 10 molar buffer solution you have prepared, which is having higher ionic strength, which is highly concentrated, less significant will be with respect to the selenate anions. So the thickness of the double layer is going to decrease. If there are more number of cations, means if the ionic strength is very low, means the concentration of the buffer is very low, the ionic movement towards the selenate anions will become prominent, will become comfortable. So thickness of the double layer will become very high. So electro-osmotic flow will increase, and hence the electro-osmotic mobility will also increase. If you use the buffer which is having higher ionic strength, which is in higher concentration with respect to cations, there is no significance to the anions such as selenate groups, because anions of the buffer are coordinating with the cations of the buffer. So there is no question of tightly binding with the selenate anions of the capillary tube. Therefore, the electro-osmotic flow can be decreased. So these are the two factors. The first factor is the zeta potential is directly proportional to the charge in the capillary walls. So it decided by the pH. pH must be always greater than 2 or 3, so that pH must be greater than always less than 2, so that the ionization of selenol groups can be avoided, and hence the zeta potential can be minimized to 0. Therefore, electro-osmotic flow can also be minimized to 0. The other factor is the thickness of the double layer. By using highly concentrated buffer of higher ionic strength, we can make insignificant the walls of the capillary tube, which is with the selenate anions, so that the thickness of the double layer can be minimized. So this is how we can play with the zeta potential in order to reduce the electro-osmotic flow. So the electro-osmotic flow profile is somewhat different from the hydrodynamic flow what we saw in the chromatographic technique. You can see here. This type of flow profile can be seen in chromatography. Because of this hydrodynamic flow, we will see the band broadening or zone spreading or channeling in chromatographic techniques. But here, the electro-osmotic flow is very different. And because of this different electro-osmotic mobility, the mobility of the ions in this manner, there is no formation of channeling or band broadening that can be minimized. And thus the separation efficiency will be more in electrophoretic technique. This is in chromatographic techniques. This type of flow is seen in chromatographic separation. This is called as hydrodynamic flow. Continual spreading of the solute band during its traveling through the chromatographic column is called as hydrodynamic flow profile. So this hydrodynamic flow profile cannot be expected in electrophoretic techniques. Electro-osmotic flow profile we can see like this. Therefore, the zone spreading or band broadening or channeling cannot be expected in electrophoretic techniques. So zeta potential, once it is minimized, the hydrodynamic profile can also be minimized, and thus the efficiency of the separation can also be enhanced. Okay, so along with the mobility with respect to electrophoresis and the mobility of the ions with respect to electroosmosis, a new term known as total mobility, which is denoted by nu total. Nu total is called as total mobility, which measures the ability of the ions of the sample and ions of the buffer at certain velocity, namely VEF and VEOF. So the total velocity with which whole ions present in the sample as well as in the buffer, they are traveling through the conductive medium is denoted as summation of electrophoretic velocity and the electro-osmotic flow or electro-osmotic velocity. VEP plus VEOF can be written as V total. So this is total velocity, this is electrophoretic velocity, and this is electro-osmotic flow. And ultimately, the total mobility, nu total, is a summation of electrophoretic mobility and electro-osmotic flow. Electrophoretic mobility and electro-osmotic flow. So by means of this equation, we can arrive to the predictions, we can arrive to the conditions that under the normal experimental conditions while performing the separation in electrophoretic technique, the total velocity for cations will be greater than the electro-osmotic velocity because they are highly charged. The charge to size ratio will be more. So the electrophoretic mobility will be more. They will move at a faster velocity. So they will elute first. Cations will be migrating at a faster velocity. Their speed is more when compared to neutrals and anions. So they are going to be eluted first. And in between the cations, charge to size ratio will be used, charge to size value will be used in order to predict the order of elution. Say lithium, calcium, aluminum, thorium, as I told in mentioning the example. Lithium is lower charged, which is having higher size, right? So it is eluted last. Thorium it is tetravalent. It is having lower size, so new EP will be more. So it is eluted first. So thorium elute first, aluminum next, calcium 2 plus next, then lithium. Okay. So for cations, the total velocity will be more, and it is more than the electro-osmotic flow. Therefore, they are eluted first. Cations will be eluted first. The total velocity of anions will be less than electrophoretic velocity. Therefore, they will elute at last. They will elute at last. Neutrals, they will be moving along with the ions of the buffer because of the equivalence of the total velocity of the neutrals to the electro-osmotic flow. They will be traveling along with the ions of the buffer, especially towards the cathode, and they will be eluted as a single band. We cannot distinguish them. But under some special conditions, by modifying the electrophoretic procedure, we can make all those neutral species to get eluted one by one. So this is going to explain you what is the order of elution in electrophoretic technique. Cations elute first, and in the group of cations, all those cations which are having larger charge to size will be eluted first, then lower charge to size. Similarly, the anions which are having smaller charge, higher size, smaller charge, higher size, they will elute at last. They will elute at last. And neutrals which are having the velocity as same as the electro-osmotic flow, they will be eluted as a single band in between cations and anions. So this is a more useful way to express the total mobility of the ions. So this slide will sum up how the elution order. As I told you, cations will elute first because their total velocity will be greater than the electro-osmotic velocity. Neutrals will be eluted as a single band because their velocity is same as electro-osmotic flow velocity. Then anions are the last components to elute, smaller, highly charged anions having the longest elution time. So among chloride, sulfate and phosphate, phosphate will be eluted last. Chloride will be eluted first. Sulfate in between chloride and phosphate, because phosphate will be having lower speed when compared to electro-osmotic flow. Therefore, it is going to be eluted last. So this is how the order of elution can be predicted in capillary electrophoresis. So we heard about the electropherogram. Just like in chromatogram we have understood. In electrophoresis, electropherogram, and the instrument is called as electropherograph. Electropherograph is electrophoretic instrument. Electropherogram is a graphical representation of the detector signal as a function of the time factor. In the x-axis, time factor will be coming, and in the y-axis, the detector signal will be coming. And that plot is called as electropherogram. What do you call the time present in the x-axis? That is called as migration time. Migration time. So this migration time is denoted by Tm. Migration time is denoted by Tm. In case of chromatography, that is retention time denoted by Tr or RT. Here it is migration time denoted by Tm. What is this migration time? You assume you are going to introduce a sample into the capillary tube. So after the application of the electric field, the ions or the solutes present in the sample will start to migrate. Soon after the introduction of the sample into the capillary tube, they will start to migrate, and ultimately they will reach the detector. They will reach the detector. Individual solute, say chloride, will take its own time. Sodium plus will take its own time to reach the detector. So what is the time taken by sodium, or what is the time taken by chloride after introduction of the sample containing sodium or chloride injected into the capillary tube, soon after the introduction of the sample into the capillary tube, to reach the detector? What is the time taken by this solute? That time is called as migration time, denoted by Tm. If you assume chloride or Na plus or Al3 plus or thorium 4 plus is traveling with a velocity of V total, where small L lowercase is nothing but the distance traveled by the solute from the point of injection to the detector. It is the distance traveled by the solute from the point of injection to the detector in the capillary tube. At the beginning, you will introduce the sample. From that particular point, where a detector is existing, what is the distance that is denoted by the L? So the total velocity taken by the total velocity of the solute, the speed at which the solute is moving, can be written as the distance traveled by the time. This time is called as migration time, where L is the distance the solute travels between its point of injection and the detector, and Tm is called as migration time. We know the velocity is equal to electrophoretic mobility and the magnitude of the electric field. Similarly, the total velocity can be written as total electrophoretic mobility or total mobility into E, means the magnitude of electric field. We know nu total is equal to nu EP plus nu EOF. Nu total will be exactly equal to nu EP plus nu EOF. So in place of nu total, you put nu EP plus nu EOF into E. Therefore, V total will be equal to nu EP plus nu EOF whole into E. So you simplify this equation, Tm is equal to L by, in place of V total, you will get nu EP plus nu EOF into E, where E is the magnitude of the electric field. And magnitude of the electric field can be written as, it is the ratio of voltage to the length of the capillary, where capital L is the length of the capillary, what length of capillary tube you are using in the operation. So finally, you substitute in place of E, V by L, you will be getting Tm is equal to small l into capital L divided by nu EP plus nu EOF into V, where small l is the distance traveled by the solute after the injection of the sample into the capillary tube. Capital L will be the length of the capillary tube. Nu EP is the electrophoretic mobility of the species, which is traveling through the capillary tube. Nu EOF is the electro-osmotic flow, and V is the voltage. If you look at this equation, in order to complete the analysis at a faster rate, the value of Tm must be greater. If the analytical time is needed to be lower, means we have to complete the analysis rapidly, the elution time or the migration time must be lower. So we can decrease this time Tm and thus the total analysis by applying a higher voltage. You can see voltage is present in the denominator. If you apply higher voltage, the value of Tm will become lower. So analytical time can be reduced, and therefore the solute can be made to be eluted rapidly. And even if the length of the capillary is short, if the length is very low, Tm is also going to be very low. If Tm is low, the analytical time will also become low. So this equation relates the migration time, the length of the capillary, electrophoretic mobility of the solute, which is having a migration time of Tm, and electrophoretic electro-osmotic flow of the buffer, and the voltage at which the electric field is generated. So this is the final expression you should remember. And unlike efficiency in chromatography denoted by number of theoretical plates, whether in GC or HPLC, whatever it is, here also we will use capital N to express number of theoretical plates. But in chromatography, we will calculate the number of theoretical plates by using the expression N is equal to 16 TR square divided by W square, where the values of TR and W can be obtained from the chromatogram. Here, we don't have chromatogram, but we are aware about the diffusion coefficient of the solute and the voltage at which we are operating the separation procedure. We know electrophoretic mobility we can calculate, electro-osmotic flow we will be knowing, and by just substituting all these parameters, the efficiency of electrophoretic separation can be written as nu EP plus nu EOF into V divided by 2D, where D is the solute's diffusion coefficient in the capillary tube. At what rate of diffusion the solute is traveling. So that is denoted by diffusion coefficient represented by D. So number of theoretical plates or efficiency of separation in capillary electrophoresis denoted by N is simply written as nu EP plus nu EOF into V divided by 2D. And in the previous expression, I told you that if you increase the value of V, means more the applied voltage, Tm will be less. And similarly, more the applied voltage, the number of theoretical plates will be more. If the applied voltage is high, the value of N will become high, then the efficiency of the separation will also become more. Therefore, the efficiency of a capillary electrophoretic separation increases with higher voltages. And if the value of N will also become very high if the value of D is low. If the solute diffusion is low, if the solute diffusion is very low in the buffer, it will be moving at a greater electrophoretic velocity. If the diffusion coefficient of solute is low, means its rate of diffusion will be low into the buffer. So it will be moving at a faster rate because its attraction towards the capillary wall is less. Therefore, its electrophoretic velocity will be high and its electrophoretic mobility is also high. Therefore, N value will also become more. Therefore, all those smaller species with highly charged, so smaller, highly charged solutes are not only the first solutes to elute, whatever the species having higher value of Q and lower value of R, they will be eluted first. Not only they are going to be eluted first, but also with greater efficiency. N will also become very high for all those solutes which are eluting first. And for all those solutes which are eluting at last, they will be suffering with respect to efficiency, separation efficiency. So here, if you look at this expression, the efficiency of the separation in electrophoresis, capillary electrophoresis, is free from length of capillary. But in case of chromatography, 16 TR square divided by W square. Directly or indirectly, the length of the column was also responsible to elute the species. So likewise, here, the number of theoretical plates in capillary electrophoretic separation of a solute is independent of the length of the capillary. The length of the capillary is not going to do anything with respect to efficiency. Whether you use 30 centimeter capillary or 50 centimeter capillary or 1 meter capillary, whatever it is, the efficiency remains same. Efficiency should not be varied, affected. So typically, we can expect 1 lakh to 2 lakhs theoretical plates, especially in capillary electrophoretic separation. So you should remember this. The migration time in place of retention time when you compare chromatography with electrophoresis. So migration time is nothing but the time taken by the solute to reach the detector after the introduction of the sample into the capillary. It is dependent upon the length of the capillary and the voltage. As the length is low, the migration time will be low. As the applied voltage is more, the migration time will become less. So analytical separation can be achieved in a short period of time. And similarly, if you apply the greater voltage, the efficiency of the separation will also become more. And even the solutes which are having lesser diffusion coefficient, they will be traveling at a greater velocity. Therefore, they are also separated, they are also eluted with greater efficiency. And approximately 100,000 to 200,000 theoretical plates can be expected. 1 lakh to 2 lakh plates can be expected in capillary electrophoresis. And we also used to express the selectivity. Say, for example, if there are two groups of solutes are present in the sample, which are having electrophoretic mobilities of nu EP1 and nu EP2, how about the selectivity of the capillary tube? Selectivity in chromatography is with respect to column. Column selectivity was explained by using the expression alpha is equal to Kb dash divided by Ka dash or Kb divided by Ka. Kb dash or Ka dash are the capacity factor of solute B and A respectively. The Kb dash will be greater than the Ka dash. If you use partition coefficients, that will be Kb divided by Ka, where Kb is the partition coefficient of solute B and Ka is partition coefficient of solute A, and also Kb will be greater than Ka. Likewise here, if there are two solutes are traveling through the capillary tube, we will be considering the electrophoretic mobility of solute 1 and 2, where nu EP1 must be greater than nu EP2. Nu EP1 must be greater than or equal to nu EP2, because alpha value will be greater than or equal to unity. The selectivity is expressed by alpha, which is used to express the separation ability of the capillary when it is used to separate variety of the solutes. So assume two solutes are going to be separated by electrophoretic technique using capillary tube. How do we express the selectivity? That is expressed by using this expression. Alpha is the ratio of nu EP1 to nu EP2, where nu EP1 is the electrophoretic mobility of solute 1, which is migrating with a greater velocity, and nu EP2 is the electrophoretic mobility of the solute 2, which is moving with a lower velocity with respect to electrophoretic movement when compared to electrophoretic movement of the first solute. Therefore, alpha value can be expected always greater than or equal to unity. So, if this alpha value is not satisfactory, means the capillary electrophoretic technique is not going to be appropriate for the separation of group of solutes. So we can manipulate the procedure. How do we manipulate this? Very simple. You know, the electro-osmotic flow is dependent on the pH. Not only the electro-osmotic flow, selectivity is also dependent on the pH. I will state one example here. You take a capillary electrophoretic technique for the separation of ammonium ion and ammonia. Okay. So you have to separate ammonium ion and ammonia. Ammonia is a neutral species. It is chargeless species. And ammonium ion is a positively charged species, which is acidic. Which is weakly acidic. Ammonium ion is a weakly acidic species with a pK value of 9.24. So, if the pH of the buffer, what you have maintained, is exactly 9.24, if the pH of the buffer you have maintained is exactly 9.24, at that particular pH of 9.24, the concentration of ammonium ion will be exactly equal to concentration of ammonia. Concentration of ammonium ion will be exactly equal to concentration of ammonia. So, we cannot distinguish the electrophoretic mobility of ammonium ion with that of ammonia. We cannot distinguish. So, we cannot initiate the movement of ammonium ion towards the cathode. So, what we have to do, in order to increase the electrophoretic mobility of the ammonium ion, we have to decrease the pH, because this is acidic. Its acidic behavior will be effectively functioning when you decrease the pH. So, if you decrease the pH lower than to 9.24, the fraction of ammonium ion present in the medium will increase. Thus, the electrophoretic mobility of ammonium ion will also increase. So, by decreasing the pH, by playing with the pH, we can increase the electrophoretic mobility of ammonium ion. Therefore, ammonium ion is easily separated from ammonia. Okay. In contrast to increasing the electrophoretic mobility of ammonium ion, by decreasing the pH, if you increase the pH greater than 9.24, where ammonia will become to be present in more fraction, because it is basic. 9.24 going to be basic pH, so ammonia is basic, so NH3 proportion will be more at the pH greater than 9.24. Hence, the electrophoretic mobility of ammonium ion will decrease. At pH less than 9.24, the electrophoretic mobility of ammonium ion will increase. At pH greater than 9.24, the proportions of ammonia will be more, therefore electrophoretic mobility of ammonium ion will be less. So this is how we can increase the selectivity. Like this, the selectivity for the separation of electrophoretic operation can be achieved by playing with the experimental conditions such as pH or ionic strength. Similarly, the next factor is going to be resolution. In chromatography, resolution can be obtained by having the relationship between the retention times and the baseline widths of two solutes. R is equal to 2 into delta TR divided by W1 plus W2. If there are two solutes are getting eluted one by one, having the retention times of T1 and T2, and the chromatographic baseline widths of W1 and W2 respectively, the resolution can be written as 2 into T2 minus T1 divided by W1 plus W2. You know this expression. So 2 into delta TR divided by W1 plus W2. So where in chromatography we will use that expression to calculate the resolution. Here, the resolution between two solutes can be determined by using the expression this one. R is equal to, R is the resolution, nu EP1 minus nu EP2 whole into V to the power of divided by square root of nu average plus nu EOF into D, where nu EP1 must be greater than nu EP2. Nu EP1 must be greater than nu EP2. This should be greater because the solute which is traveling with the greater velocity must be considered in order to calculate the value of nu EP1 because it is traveling with greater velocity. So the electrophoretic mobility of the species which is having greater charge and smaller size is denoted by nu EP1 minus nu EP2. This is the electrophoretic mobility of the solute 2, which is moving with the lower velocity than the solute which is moving with the velocity and the electrophoretic mobility of nu EP1 into V to the power of, where V is the applied voltage, at what voltage we are operating the separation process. Nu average is nu EP1 plus nu EP2 divided by 2, average, nu average of electrophoretic mobility of both the solutes. Nu EOF is the electro-osmotic flow or electro-osmotic mobility of the buffer medium. D is the diffusion coefficient of the solutes, diffusion coefficients of the solutes. So this is the expression we will use to calculate the resolution. So resolution can be denoted as nu EP1 minus nu EP2 into V to the power of divided by square root of nu average plus nu EOF whole into the diffusion coefficient of the solute. So if you simply increase the voltage, resolution can be increased. And if you decrease the electro-osmotic flow, resolution can be increased. So resolution is directly proportional to the voltage or inversely proportional to the electro-osmotic flow. And even increasing the electro-osmotic flow improves the analysis time. You do remember. Electro-osmotic flow, once it is increased, the movement of the solutes along with the buffer will become rapid. So analytical time will be reduced. But if the value of nu EOF is more, the value of R is going to be impaired. The value of R will be lesser. So resolution is going to be impaired if the electro-osmotic flow is more. If we have set the electrophoretic separation procedure in such a way that the highly concentrated buffer you have used, that highly concentrated buffer will become consequent to increase the electro-osmotic flow. This increased electro-osmotic flow will become responsible to reduce the resolution. So if the resolution is impaired, if the resolution is lower, that procedure is going to be useless. So you do remember, by increasing the voltage, you can increase, you can decrease the migration time, and therefore the analytical time can be reduced. Not only the migration time can be reduced, but also the resolution can be improved by increasing the voltage. And if you decrease the nu EOF, the electro-osmotic flow, the average electrophoretic mobility of the solutes will be ultimately increased, therefore ultimately decreased, therefore the resolution will also become increased. So resolution will be satisfied if you have set the voltage at an appropriate value and the electro-osmotic flow is very less. So this is all about the theory and some important equations which are very essential we have to use in electrophoretic separation procedure.